Welcome to another video on the Math Exploration Tour. Today we are going to establish a relationship between two seemingly unrelated things. One, the Fibonacci numbers, and two, the Pascal's Triangle. Why do Fibonacci numbers appear in the Pascal's Triangle? Watch on to find out. Fibonacci Sequence and Pascal's Triangle. Consider the following sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. Notice that starting from the third term, each term is the sum of the two previous terms. That is, we start with 1 and 1, then we have 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 equals 13, and so on. We will denote the sequence by Fn. For convenience, we will let F0 equal to 1, F1 equal to 1, and Fn equals Fn minus 1 plus Fn minus 2 for n greater than or equal to 2. The Pascal's triangle is a triangular array of the so-called binomial or combinatorial coefficients. The nth row and the kth column of the Pascal's triangle contains the number C of n, k, otherwise denoted as n choose k, which is popularly known as n factorial divided by k factorial into n minus k factorial, or otherwise also famous as the coefficient of x to the k in the binomial expansion of 1 plus x to the n. Fibonacci sequence in the Pascal's triangle. Consider the following diagram of the Pascal's triangle. We will see the diagonal entries of the Pascal's triangle. The 0 at the diagonal contains a single entry 1, that is 0 choose 0 equals 1. It is convenient to start with 0. The first diagonal also contains a single entry 1, that is 1 choose 0. Hence 1 choose 0 equals 1. The second diagonal contains two entries, that is 1 and 1, namely 2 choose 0 and 1 choose 1, which sum up to 2. That is 2 choose 0 plus 1 choose 1 equals 2. The third diagonal also contains two entries, namely 1 and 2, that is 3 choose 0 and 2 choose 1, which sum up to 3. That is 3 choose 0 plus 2 choose 1 equals 3. The fourth diagonal contains three entries, 1, 3, and 1. That is 4 choose 0, 3 choose 1, and 2 choose 2, which sum up to 5. Thus, 4 choose 0 plus 3 choose 1 plus 2 choose 2 equals 5. The fifth diagonal contains three entries as well, namely 1, 4, and 3. That is 5 choose 0, 4 choose 1, and 3 choose 2, which sum up to 8. Thus, 5 choose 0 plus 4 choose 1 plus 3 choose 2 equals 8. By observing the pattern, we can see that the nth diagonal contains the entries n choose 0, n minus 1 choose 1, n minus 2 choose 2, and so on. How many entries does the nth diagonal contain? The 0th and the first diagonal contain a single entry. The second and the third diagonal contain two entries. The fourth and the fifth diagonal contain three entries each. Hence, by observing the pattern, the nth diagonal will contain floor of n by 2 plus 1 entries. Here, the floor function, also known as the greatest integer function, returns the greatest integer which is lesser than or equal to the input. Thus, the nth diagonal contains floor of n by 2 plus 1 entries, namely n choose 0, n minus 1 choose 1, n minus 2 choose 2, and so on. By observing the pattern, we claim that the following identity holds in general. N choose 0 plus n minus 1 choose 1 plus n minus 2 choose 2, and so on, floor of n by 2 plus 1 such entries otherwise denoted by shorthand notation as summation I equal to 0 up till floor of n by 2 of n minus I choose I, must be equal to the nth Fibonacci number. The steps problem. A man wants to climb n steps, but he can climb only one step or two steps at a time. In how many ways can he do so? We are going to count this number in two ways to prove the Fibonacci number's identity. In other words, we will give a combinatorial argument to prove this identity. Method 1. Using recurrence relations. Let an be the number of ways the man can climb n steps. Note that a0 equal to 1 holds in trivial. A0 is the number of ways the man can climb 0 steps, which in fact is trivially 1 because he needn't do anything at all. A1 is the number of ways the man can climb one step, which he can do in one way. That is, take a move of one step. There is no other way. For n greater than or equal to 2, we divide the counting into two cases. Case 1. The man starts with a one-step move. Notice then that the man would have to cover n minus 1 more steps, and the constraint that he can do so by only a step, one step or two steps at a time holds as well. So by definition, he can do it in an minus 1 ways. Case 2. The man starts with a two-step move. Notice that the man then has to cover n minus 2 more steps, and the constraint that he can do so in only moves consisting of one steps or two steps again holds. So by definition, he can do it in an minus 2 ways. Now by the addition principle, it is clear that we must have an equals an minus 1 plus an minus 2 for n greater than or equal to 2. And thus we get the Fibonacci sequence an equals fn. Method 2. Using direct counting. An is as defined in method 1. Further, let S1 denote a move of one step and S2 denote a move of two steps. Suppose the man takes I S2 moves. He has completed 2I steps. So then he has to take n minus 2I S1 moves so that in total he covers n steps. These S1 and S2 moves may be in any order. Thus, our task is to arrange n minus 2I S1s and I S2s, because each such arrangement corresponds to a different way the man can climb the n steps. This can be done in n minus 2I plus I factorial divided by I factorial into n minus 2I factorial by high school mathematics. This is just a disguise for n minus I choose I. What are the possible values of I? If the man takes I as 2 moves, then he has completed 2I steps, but he can complete at most n steps. So 2I must be lesser than or equal to n. So I can be 0, 1, 2 up till floor of n by 2. Observe that I can take each one of these values. Hence, by the addition principle, we have an equals summation I equal to 0 up till floor of n by 2 of n minus I choose I. Thus, we have established the relation between the Fibonacci numbers and the Pascal's triangle by proving the beautiful identity summation I equal to 0 up till floor of n by 2 n minus I choose I equals fn, where fn is the nth Fibonacci number, by proving that each one of them is equal to an, where an is the number of ways a man can climb n steps with the constraint that he can take only moves of one steps or two steps. Thank you for watching this video. I request the viewers to share this video to all math enthusiasts. For more math, please subscribe to my channel.